With our remaining applications, we work towards prime factorization. For this, we will have to find the period of a certain function, which can indeed be done very efficiently on a quantum computer using phase estimation. For our preparation, I will first describe a very general method to find such periods, which is known as period finding. And then we are going to turn to a very specific function and a certain mathematical problem, which is known as order finding. And mathematically, finding these orders can be used as a tool to factor numbers into prime factors, and therefore this leads us then to prime factorization. And the algorithm that we then end up with is known as the Shor algorithm. When we set up these algorithms, we quickly recognize that we also need some elements from number theory. Not very complicated aspects, but some aspects nonetheless. We will need these aspects also when we then look at some very concrete examples that show us how these algorithms really work in practice. But they appear also in the most general setting, and indeed already towards the end of our discussion of period finding. When we want to understand how period finding really works, we actually need continued fractions. But this is already the most complicated thing that we will need from there. So this will then be a good point to collect everything that we need from number theory. Both to conclude our discussion of period finding as well as to prepare everything else. These preparations indeed basically define of how we have to proceed from there. So the remainder follows quite naturally, and we can illustrate everything by concrete examples. So let us turn to period finding and start here. So let us start with period finding. Here we assume that we are given a function f of x, where x is an integer and f is an integer as well. And this is periodic with a certain period r. So we want to determine this period r. And what we are going to use is the corresponding function gate. So we assume that this function gate is accessible to us, so this must be given. Our function can be very general, so there will be n bits of an input, and this is being memorized by the function gate, while the bits down here implement the output, which might have n prime bits, and we do it in this way here. And now it sounds like a good idea to try and test this function for all possible arguments at the same time and see whether a systematic pattern appears. And this we can do again as in other algorithms by starting out with a computational basis state where all these quantum bits are in the state 0, and then we apply Hadamard gates to all of them, so that we end up in this state capital psi at this point here. In the remaining bits, we now want to directly capture the values of the function. So we start in this state here and then indeed do not apply anything to them, so that y at this point here is just 0. And therefore at this point we just obtain f of x, and the state that we then end up with is this superposition here. So for each computational basis state of the first n bits, we have brought the remaining bits into the computational basis state corresponding to the value of f of x. Let us denote this state in some suitable way, say as phi. And now we can rewrite this state approximately and I will invest some time of explaining in why this is an approximation, as another sum of states, where we here have a sum running only over r different contributions, n going from 0 to r minus 1. And in here we have two states that are somehow related to the quantum Fourier transform. I'm first going to write down the result and later I will derive it. Well, what we have here is essentially the n-bit approximation of the fraction n divided by r, where n is this index here and r is the period that we're interested in. And indeed at this stage here, this is the quantum Fourier transform of that corresponding state. We will unravel this in a minute. And here we will have a new state, which I denote in this way here. I will derive this in a minute and will also define then all the terms, but let me first tell you where this leads to. Namely, this means when we run these quantum bits here through the inverse of the quantum Fourier transform, we end up with a new state. Let's call this one here phi prime. So obtained by the inverse of the quantum Fourier transform. And this now looks very similar to what I've just written here. But now instead of the quantum Fourier transform, we have now this n-bit approximation of this fraction here. And when we then make a measurement, we obtain these numbers here, and from these we can then reconstruct this period r. So there are basically two things left. We need to derive this expression here and define all the terms in there, and indeed also understand why this is an approximation. And then we need to understand of how we can use these numbers here to reconstruct r. And this is indeed very closely related to why this one here is an approximation. So let us start with the derivation. For this, I first write down the state phi here in the form that it originally appeared. So with this sum here over x, running over all possible values in the computational basis, and the quantum bits in the corresponding state, and the remaining quantum bits in the state f of x. And you see that I left some space, and this is so that I can include some additional terms. And the first one is the sum over an integer n running from 0 to r minus 1, where r is the period that we want to find. And in here I'm going to include another sum over an integer z running from 0, but now again over all values in the computational basis. And then I include in here some suitable exponential factors, namely this factor here, where z appears, and this is then multiplied by a certain fraction, which I write in a suitable form. And here I include a corresponding factor, which has a minus sign in front and involves x, and here I'll just write this fraction as n divided by r. And when one then looks at everything which I've written down here, one realizes that this is only finite when z is equal to x, and overall this sums then to 1. Which means that we can just insert everything up here, and in addition, wherever x appears, we can replace it by z. And we do it at this point here. So then we obtain the following expression. And in here we can then group terms together depending on whether they depend on x or z, and also suitably distribute some factors. So in here we have two groups, one for our first n quantum bits and another one for our remaining ones. And well, for these remaining quantum bits, this is just some state which depends on little n, but we're not going to make use of these quantum bits anymore in this algorithm, so we just call this state f hat of n. And when we then look at the state of the first n quantum bits, then we see that this looks very similar to the outcome of the quantum Fourier transform applied to one of the computational basis states. This would be the case if this number here would indeed be an integer. But in general, this is just a rational number which is very well approximated by this n-bit integer, and therefore we end up very close to the result of the quantum Fourier transform applied to this computational basis state, where we just take the integer part of this rational number. So this is then of the form as given above, and therefore completes our derivation and definitions. It also explains why this is an approximation, and at the same time highlights that there is one additional task. Because when we then run this state here backwards through the quantum Fourier transform, and finally make a measurement to obtain a value x, then we have to interpret this here as the integer part of this rational number. Practically, this means that n divided by r is very close to x divided by curly n. So we could basically stop here because it is clear that this gives us some information about little r, but it is worthwhile to see how we can exactly extract this information. In here, curly n is a very specific number, and in particular an integer power of 2. So this will turn into an equality only in very special cases, for instance when r is also such a power of 2. Therefore it would be nice to have a systematic way to make use of this approximation. As this is an approximation involving rational numbers, this can be done using continued fractions. Therefore, from this point we will also need some tools from number theory, but fortunately not very complicated ones. So let us have a brief look at these continued fractions and then collect some further number theoretical results that we need a little bit later on.